So in this section, we're going to look at semiconductor heterojunctions, which means the joining of two different semiconductors together at an interface. So without talking about the doping first, we'll just look at how those band gaps could align at the interface. So the first type, conveniently called type 1, is such that the larger band gap overlaps the smaller one both in the conduction band and valence band. So if we connect these lines here, we would have a delta EV and a delta EC. And if we add up those two, we're going to get E gap 2 minus E gap 1. So a classic example of this would be germanium to silicon. Another one is gallium arsenide to aluminum gallium arsenide. Okay. The second type, also conveniently labeled as type 2, sometimes called the staggered band gaps. In this case, we would say delta EC is positive, while delta EV would be negative. And if we draw here the absolute value of this, it's okay. Now, when we would still use this equation to define them, but remember that delta EV would be negative here, and in this case, we would have delta EC being the one that's negative and delta EV being the one that's positive. The third and last case, you guessed it, it's called type 3, is the so-called broken gap case. In this case, you can imagine a very, very large delta EC. In fact, delta EC, which is bigger than the E gap of the second semiconductor. And then a very large negative delta EV to bring that equation into agreement. The sort of canonical example of this is indium arsenide, gallium antimonide, which is used sometimes in infrared detection and emission. So now we know what the interfaces are going to look like, where the conduction bands line up, which is going to be determined by their electron affinities. The next part is to figure out the electrostatics, built-in voltages, and the band bending associated with doped semiconductors of any of these types. Okay, so as our first example, let's look at an NP heterojunction. And some convention, this could be written as NP like this, lowercase, uppercase, to denote that the p-type doped side has the larger band gap. So if you have the E gap 2, you write, the E gap 2 being larger, you write that one as a capital letter. And you could also have an NP heterojunction similarly if we reversed these but kept the dopings the same. So what's going to happen when we put these materials together? Let's look where the Fermi levels are first. So the Fermi level on this one is here, and the Fermi level on this one is here. So to bring them into alignment, we know that we're going to have band bending that satisfies the movement of the two Fermi levels like this. But what we're going to enforce is that these connection points remain the same, so that we're maintaining the delta EC and the delta EV in our final diagram. So what does that look like? So we know they have to move like this. So our n-type side has to have band bending that goes down like this. Or if we're coming towards the interface, we could say it's going up, and it forms a depletion with ionized donors. Then on this side, we'll have our larger band gap material. And again, the movement is like this, so that the opposite sense of band bending is induced in the larger gap material. Again, a depletion width is formed with Na minus density of dopants, ionized dopants. Then we can come in and draw a constant Fermi level across. So notice that we've maintained these delta EC and delta EV values. And we can figure out what those values are going to be if we know the electron affinities of these two materials. So this would be chi semiconductor number 2. This would be chi semiconductor number 1. And this is so the difference between chi 1 and chi 2 is going to give you the delta EC. Then you can figure out the delta EV by taking the difference of the sums of chi 2 plus E gap 2 and chi 1 plus E gap 1. And you'll notice that that comes out to this distance right here. So what's different and what's similar to our normal PN homojunction? Well, what's similar is that the band bending and the formation of depletion widths proceeds in the same manner. What's different is that we have to account for these band offsets. So this is the conduction band offset, and this is the valence band offset. And also we have to account for the fact that the dielectric constants might be different in the two sides, as well as the doping. So what I like to do is figure out how to write equations so that you can figure out how big the band bending is, what the built-in voltage is, etc. So let's do this. Let's start here at point 0. And if we go from point 0 up to the conduction band, we can define this as E phi n. So this is the distance from the Fermi level to the conduction band on side 1. Then from here to here is going to be the built-in voltage, EV built-in on the n-type side. So we could say this is point 1, this is point 2. If we slide over here and we move up to point 3 here, we've added this value, delta EC. And then if we move far away from the junction and we move up to this point here, this is going to be E phi n on the second side. That's on the one side. So now we're at point 4 here. So now, to go around a complete loop, we could move back down from the conduction band down to the valence band. So that would be the band gap of the larger material. That's 0.5. And then we could move back up to the Fermi level, making this complete loop because we've come back to the same value that we started at. 0.6. So this additional little piece here would be E phi p 2. And then this is E gap 2. Okay, so now let's look at how to write an equation that will allow us to relate the band bendings, the dopings, and the band offsets in one of these heterojunctions. So I'm going to outline a general procedure And the procedure is to write an equation where all of the components add up to 0. And we're going to get this sort of like a Kirchhoff's voltage law by going around a closed loop and arriving back at the same energy we started. So let's start here at the Fermi level on the n-type side, which has the smaller band gap. So if we start here at 0, we move to 0.1 here. Well, we've gone up an amount given by this. So we're going to start our equation here, E phi n1 plus. So the next place we go is from 0.1 to 0.2. If we do that, we've gone up by the built-in voltage on the left-hand side, or semiconductor 1 here, which is also the n side. If we slide over to here, staying at the same energy, the next thing we can add is delta EC. Then if we come over here far away from the junction, this distance here, moving us up to the conduction band on the second side with the larger band gap, is going to be the built-in voltage on the second side. Now we're going to start moving back down to close our loop. So we're starting here at 0.5, and we're going to go all the way down across the band gap to get here to 0.6. So we're going to do minus E gap 2. Then we're going to come back up, and this, I went past this point before just to make convenient, to use the convenient value of the second band gap. We're going to come back up this amount, which is given by the distance of the Fermi level on the p-type side, to the valence band edge. So we're going to add another piece here, which is E phi p on the second side. Now we've actually completed our loop because we can slide over at the same energy back to 0.0 where we started. So we've gone around this loop and we've created an equation here which we can use to relate any of these values. And I'll just highlight again, how do you calculate these phi values? Well, we can get this here from P over NV2 has got to equal exponential to the minus E phi P2, over KBT. So we're using our equations that we originally used for the carrier densities to turn those into distances on the band diagram. So in this way, we can go around loops through any heterojunction and create a master equation which we can use to figure out different components. So one important quantity here that we didn't solve for explicitly is the total built-in voltage. So if we add these two parts together, we could get the built-in voltage, and we could move everything else to the left-hand side and get an expression in terms of these quantities. Now it turns out our rule for where built-in voltages come from that we mentioned in terms of the Schottky barrier still holds here. So if we first, without even doing anything else, look at the original isolated band diagrams, the work function for the one material and the other material is going to, the difference in work functions is going to determine the total built-in voltage. So if we have E, V, built-in total, this is going to be the difference in these two, so E phi 2 minus E phi 1. So we can drop the e's here and see that the work function difference is exactly the total built-in voltage. So there's relationships, obviously, between the distance between the Fermi level and the band edge and the semiconductor electron affinity and then the semiconductor's work function. So we can plug those relations into this master equation and relate any of the properties that are unknown in a given problem. So next we're going to look at some more examples of what the band diagrams look like in a couple of different cases. So first, a word about what happens to the vacuum level. So when we introduce the band bending in this N capital P junction that we were just talking about, what actually needs to happen is that the vacuum potential bends like this. And this is a consequence of assuming that our electron affinities remain the same. And that our Fermi level is constant throughout the band diagram. So this again was for an N-P junction like this. So this is actually the same case as what happens in a PN junction, just where you have two different chi's on either side here. So in this case, it'd be EVAC, EC, and we would, of course, have the same chi for if we have the same material on both sides for our normal NP junction, like this. So this is the silicon example. This could be the germanium silicon example. Another interesting consequence of these heterojunction band diagrams is that sometimes you can pull large densities of carriers up against a barrier. So we saw a little bit of this happening in the ohmic contact that we talked about just recently. And what I want to point out is the distance, the local distance between the band edge and the Fermi level is going to determine the number of carriers here. So if this distance is smaller than out here, it means more holes will accumulate at this little notch in the band diagram here. So in this case, the holes are the minority carriers on the N-type side, so there aren't that many of them, and they don't change the band bending at all. Now, it turns out if you make what's called an isotype heterojunction, so the classic example is N-type gallium arsenide in contact with N-type aluminum gallium arsenide. So the band alignment is type 1 like this. And if we make both of them N-type, the Fermi level will be here in this one and here in this one in the beginning. But then we have to align the Fermi level still, but maintain this band offset, delta EC. So upon joining them, this diagram is going to look something like this, actually. And I'm just drawing the conduction band edge. Now, by our same argument, this point right here is very, very close to the Fermi level. And so now we have quite a few electrons piling up inside this little potential well. And those electrons are going to be pulled from somewhere on both sides of this junction, because both sides are doped N-type. Now let's look a little more carefully at this well, especially if the well is narrow and deep. So if we have a large delta EC and a large doping on the left-hand side, we can actually make a very small well, small enough that we actually have to consider it within quantum mechanics. So similar to what happens inside the finite square wells that we talked about before, now we're going to look at what happens inside a triangular well, and you get some set of energy levels. We won't go into the details of what these values of the energy levels are, but suffice it to say they will be quantized. So we'll get quantization of the allowed energy levels for the direction normal to the interface. Now, however, in the plane coming out of the board, the semiconductor will still behave as if in bulk. So really you have a very thin layer of very high charge density, or a sheet charge. And this is given the term two-dimensional electron gas, or 2-deg, which will form at this interface. And depending on the doping, the electrons in the 2-deg will either occupy the E1 state, or sometimes the E2 state, or higher states, depending on the amount of electrons that are donated into the well and what the spacing between the energy levels is. But the interesting physical effects arise from the fact that these electrons are confined to move in a two-dimensional plane instead of a three-dimensional volume. And this has actually led to some Nobel Prize-worthy discoveries. So in this section, we've qualitatively described the band diagrams of semiconductor heterojunctions. The expressions for the depletion widths are very similar to those for the normal p-n junction, just with the substitution of the correct dielectric constant for the material 2 or material 1, depending on if you're talking about the n-type or the p-type depletion width. The built-in voltage is still going to be given by the difference in work functions, and if you think about it in those terms, you can use that rule across all heterojunctions, be they semiconductor, NP, PN, or metal semiconductor junctions. And then finally, the behavior under applied bias in terms of current is a bit more complicated when it comes to semiconductor heterojunctions. There are some components you can imagine trying to flow current this way with electrons. You would have to overcome this barrier. So there are aspects of thermonic emission. However, it turns out that also drift and diffusion have to be included. So the treatment is quite advanced and not given in most introductory textbooks. So we won't worry about it too much here, except to say that they'll still behave as ideal diode forms, but the details of what goes into the J0 is more complex. So that'll wrap up our discussion of semiconductor heterojunctions for today.